So in this lesson, we're going to use our function notation from the last lesson. So notice we have f of x, g of x, h of x, and we're going to use this just to reintroduce some functions that you're already familiar with and talk about the differences between them and how to recognize them in the wild. The first thing we're going to do is actually just complete a table for each one. I'm guessing, I heard you guys already know how to do this. So if you feel like it, you can pause the video now and just complete the table. If not, you can continue to watch. I'm going to give you an example for the first row or two for each, and then I'll fill out the table in the video as we play. So f of negative 1 would be 2 times negative 1 plus 2, which would be 0. So that's all we're doing here is plugging in each x value. My next one, when I plug in 0, I'd get 2. My next one, when I plug in 1, I would get 4. And then when I plug in 2, I would get 6, and then 8. So that's my linear function. So this is the one that's probably the most familiar to you. And then my exponential function, g of negative 1, means plug in negative 1, but now it's the exponent. Make sure you write that clearly. And this ends up spitting out 2. And then plugging in 0, we get 4. Plugging in 1, we get 8. And so on and so forth. So what we're studying here is the pattern. So already you're probably seeing the pattern for f, for g. And then for h is our quadratic. So h of negative 1 would be 3 times negative 1 squared. And you guys know squaring a negative makes a positive, but I still see people making this mistake. So just make sure you pay close attention to your signs when you're squaring a negative number. Here we get 3. Here we get 0. This one's going to be interesting, right? Here we get 3 again. And then 2 is going to spit out, well, 2 squared is 4 times 3 is 12. And then 3 is going to spit out, 3 times 3 is 9 times another 3 is 27. Okay. So make sure, if you're unsure how I got any of these numbers, I think this should not be rocket science for you guys, but make sure if you're unsure how I got any of these numbers, you ask me in class. What we are looking to analyze here is how each of these is changing. But before we do that, I do want you to just take a look at the examples I gave you of where these show up in real life. So the reason we're studying these and we want to be able to recognize these is because we can use all these things to model different things that we don't run into in real life. For example, you guys may or may not know that I like to race bikes. You probably don't know that about me at this point of the year, but wind resistance. So like when you're driving in a car or when you're riding a bike, the wind pushing against you is a quadratic phenomenon. So that means that as you go faster, the wind pushing against you gets harder and harder. It's not just a linear relationship, so that's why bike racer people wear these weird spaceman helmets sometimes for aerodynamics to make the wind resistance easier. You should also know at this point in your math career what the graphs of each of these look like. So I'm just going to draw a little sketch of each of these. So the graph of a linear function is a straight line, increasing or decreasing. Exponential starts kind of flat and gets very steep. It increases at an increasing rate, or also it could decrease at an increasing rate. Quadratic, is a parabola, either a happy parabola or a sad parabola. So just make sure you can recognize those graphs. I think that should be familiar to you. All right, now let's consider our rates of change here. So what I mean by this is how we get from one y value to the next, right? So notice I add 2, I add 2, I add 2 here, and 2 is my slope. Right, so linear functions have an additive rate of change, or sometimes we call that a constant addition. And you guys know that the word for that constant addition is the slope of the function. Then my exponential function, notice here we're doing times 2, 4 to 8, times 2, and times 2. So that is no longer an additive relationship, it's a multiplicative relationship, right? And sometimes that's called the common ratio, or the common multiple. But really it's just the number we're multiplying by to get to the next y value. Delta Math uses this language a little bit in your homework. And then my quadratic function, look what's happening here. So here I'm doing plus 3. Here I'm doing plus 9. Here I'm doing plus 15. And it's a little bit harder to see this pattern. But something really interesting happens if I analyze what I'm adding each time. And you maybe did not know this about quadratic. So here plus 6. Here plus 6. So I'm adding 6 each time, right? And if I wanted to figure out what my next value was, well, I'd add 6 to 15, so it'd be plus 21, and that would give me, what, 48, right? Yeah, 48. So that's how to recognize a quadratic function. So sometimes these are called the second differences. I don't need you to know this vocabulary, but I do need you to be able to recognize the table. The second differences are linear, or are increasing additively. Great, so that's 3 basic functions, what their graphs look like, and how they change. By the way, if you take calculus with me next year, the first half of the course is all about rates of change. So things like slope and how functions other than lines are changing. Now, we're just going to do a couple of quick examples so that we can recognize these in the wild in real life context. Remember, that's why we're doing this. Take a second to read just my first word problem here. I'm going to trust that you're going to read it. I'm not going to read it to you. And notice my graph is linear. It's made of lines, but it's not just a linear function. It's what's called a piecewise linear function, and we'll study these more in detail a little bit later. But notice it gives us distance in time, and the question is, what time did you leave Noble based on the graph here? Well, one thing we might do here is annotate the graph. Remember, y is our distance from home, and we might break our graphs into increasing intervals. So here we have another increasing interval. And then we have a decreasing interval over here. And then our last type of interval would be, let's not use green again actually, what is called a constant interval. Hopefully you've seen these words before, so that's a constant interval. And then here's a constant interval down there. And this, again, just refers to how the graph is changing, so whether we're going uphill, downhill, or staying the same. And in this context, right, driving to Noble to get new shirts, again, constant means stopped, right? So your distance from home is not changing. So that means the second time you stop, according to the text, is at Noble, right? So Noble is here, right? Stopped at Noble. So if the question is, what time did you leave? Well, it's this time, and it looks like 16 minutes, where we go from a constant distance from home, so not moving, to a decreasing distance of home. So the answer here would be 16 minutes. After you leave home, you start to go home, because we go from a constant rate of change to a decreasing rate of change. And then here we have an exponential function. So the news of your prom date is spreading like wildfire here. And if we made a little list of how many people know, so we could make a little table. So we have time versus number. So in the first minute, you tell 2 people, they tell 4 people, who tell 8 people, who tell 16 people, and so on. So that's an exponential relationship. That's a common multiple like we discussed up here. So my graph of people versus time should be that kind of upward increasing curve that we know exponential graphs make. Okay. So there's our first 3 little families of functions. We're going to review exponentials and quadratics in a little bit more depth later in the year.